So section 1.5 covers linear inequalities in one variable. So they're like linear equations, except instead of an equal sign, they use a less than, greater than, less than or equal to, or greater than or equal to symbol. And they also can have many more solutions. Typically, we just would have x equals 4, right? But now I could have x's, But now I could have x is less than 4, greater than 4, less than or equal to, or greater than or equal to 4, right? And that would have many, many solutions. So we're going to need to graph these solutions on a number line. So when we solve an inequality, what that is the process of finding the set of numbers that make our inequality a true statement. And that set of numbers, it's going to typically be more than just one number, is called our solution or our solution set. And these numbers that we find in our solution set, all of them are said to satisfy our inequality. Friendly reminder that we want to express our solutions in interval notation, right? Interval notation uses square brackets to indicate if the endpoints are solutions. That'd be used with greater than or equal to or less than or equal to. Parentheses represent that our endpoints are not included in our solutions. That's used with greater than or less than. So here, for example, we have all numbers less than 0 and all numbers greater than or equal to 4. It's important to note that infinity and negative infinity always get parentheses. So how do we solve a linear inequality? We're going to follow the exact same steps we would for solving an equation. So we need to simplify our algebraic expression on each side, right? We have to combine like terms. Then we use the addition property to put all of our variables on one side and the constants on the other. Next thing we want to do is we want to isolate our variables, so get it to have a leading coefficient of 1 and solve. The only thing that's really different here that other than how we express our solution set is that if I have to multiply or divide by a negative, I have to flip my sign. So instead of having greater than, it becomes a less than, and less than or equal to becomes a greater than or equal to. We flip the symbol. Then what we want to do is express the solution set in interval notation. So we'd graph the solution on a number line. Now, I always like to do this because it helps me visualize the solution set. And you can draw like the world's fastest number line. It doesn't have to be pretty. It just has to get the job done. So let's go ahead and solve these following equations and write them in interval notation. So here I have x minus 7 is less than negative 12. I'm going to go ahead and add 7 to both sides. That gives me x is less than negative 5. So I'm going to have a number line. Here's a blank one. So here's negative 5. I know to the right is bigger, to the left is smaller. You don't have to fill out the entire number line. Now you can go ahead and graph your solution. I'm going to go ahead and say, okay, negative 5 is my endpoint, but it's not included, so I'm going to use an open circle. And I say that x is less than negative 5. So let me pick a test point. I'm going to pick negative 6. Negative 6 is less than negative 5. That's a true statement, so I'm going to shade to the left over here. In order to write this in interval notation, I read from left to right. That gives me negative infinity, comma, negative 5, parenthesis, because my endpoint is not included. Next, I have negative 4x is greater than or equal to 28. I'm going to go and divide both sides by negative 4. That gives me x is greater than or equal to, less than or equal to, right? Because I have to flip the sign. Less than or equal to 28 over negative 4, which would be negative 7. So x is less than or equal to negative 7. So here I have negative 7, negative 6, negative 8. Make the number line work for you. I have less than or equal to, so I know my endpoint is included. I'm going to put a closed circle on negative 7. X is less than or equal to negative 7. Okay, so negative 8 is less than or equal to negative 7. So I'm going to go ahead and shade to the left. Next, I have negative 3. Oops, let's change colors. times x plus 4 plus 2 is greater than or equal to 7 minus x. So let's go ahead and simplify both sides. This gives me negative 3x minus 12 plus 2 is greater than or equal to 7 minus x. Then I'm going to go ahead and say I have negative 3x minus 10 is greater than or equal to 7 minus x. I'm going to go ahead and add 3x to both sides. So I get negative 10 is greater than or equal to 7 plus 2x. I subtract 7. I get negative 17 is greater than or equal to 2x, and then I have to divide both sides by 2. So that gives me negative 17 halves is greater than or equal to x. So here, negative 17 halves, that's really close to 9. So I've got negative 9, negative 8. Here's negative 17 halves. I know my endpoint is included, so I'm going to graph it with a closed circle. And I have that x is less than or equal to negative 17 over 2, so I'm going to shade to the left. This wasn't a really exciting set of examples, right? All of them look pretty similar. But if it had been greater than, we just would have shaded on the right. Now we're going to work with these types of inequalities. Sometimes these are called compound inequalities. So what's different about those is instead of having one equality symbol, I have two. Inequality symbol. So if I want to write the solution for this in interval notation and graph it on a number line. Now, because I have three pieces, instead of what I do to one side, I do to the other, what I do to the middle, I do to both sides. So I'm going to go ahead and subtract 2 to isolate my variable, and I do that from the middle and the left and the right. So I've got 1 is less than x, which is less than 6. So this is my solution set. I have all the numbers where x is greater than 1, but x is less than 6. So here I've got 1, 2, 3, 4, 5, 6. Let's go ahead and label 0 just for kicks. So I know my endpoint is 1, but 1 is not included, so I'm going to draw an open circle. My other endpoint is 6, but it's not included, so I'm going to draw an open circle. And x is between these two numbers, so it's going to be any value in here. It could be pi, it could be 4, it could be 9 halves, right? Any of those numbers make this a true statement. So my solution set goes from, if we read left to right, parenthesis, 1, comma 6, parenthesis. Now let's try the next for negative 2 is less than or equal to negative 3x minus 1, which is less than or equal to 5. I'm going to go ahead and add 1 to the middle, to the right, to the left. I get negative 1 is less than negative 3x, which is less than or equal to 6. Then I go ahead and divide both sides by negative 3. Whereas before we flipped the sign once, now I got to flip two signs. So I have a positive 1/3 is greater than or equal to x, which is greater than or equal to negative 2. And see, this sentence makes sense, right? 1/3 is greater than x, which is greater than negative 2. If I hadn't flipped my signs, I would have had 1/3 was less than or equal to x, which was less than or equal to negative 2, and that doesn't really make sense. So it's important for us to check our work. I'm going to go ahead and plot this. I've got negative 2, negative 1, 0, 1, 2. I have 1/3. That's going to be right about here, right? And it's included, so I'm going to fill that in with a whole dot. My other endpoint's negative 2. I go ahead and I know x is between the two. So my solution set is bracket negative 2, comma 1/3, bracket. And any value of x between these two numbers would make this inequality a true statement. There are some inequalities with unusual solution sets. So for example, x is greater than x plus 1. Let's see why this has no solutions. 0 is greater than 1 is what happens when I combine my variable terms. Is this a true statement? Is 0 greater than 1? No, it gives us a false statement. If you end up with a false statement, there are no solutions. This next example is going to have infinitely many solutions. What do you guys think my solution is going to look like? If my top one was false and there was no solutions, what's this one going to be? Let's go ahead and find out. I'm going to go ahead and distribute. I have 3x plus 3 is greater than or equal to 2x, and x becomes 3x plus 1. Subtract 3x. I get that 3 is greater than or equal to 1. Is this a true statement? Yeah, this is true. This means no matter what I substitute in for x, be it the square root of 2, be it negative 1/2, be it 5/3, or a million, I'm going to simplify down to this and always get a true statement. So this has infinitely many solutions. Typically we write no solutions like this, or you could just write out no solutions. Infinitely many solutions you can write as negative infinity to positive infinity, right? Because that would be the entire number line. Or you could just write out infinitely many solutions. The choice is yours.